From Here to the Stars, a video series created by the Tennessee Valley Interstellar Workshop. The TVIW is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. I am your host, Euin Cobb. Our guest today is Dr. Philip Lubin, professor of physics at the University of California, Santa Barbara. Dr. Lubin is co-recipient of the 2006 Gruber Prize in Cosmology, along with the COBE science team for their groundbreaking work in cosmology. He has published more than 200 papers. Here is Dr. Philip Lubin. You are a NASA Institute for Advanced Concepts Fellow for your work on laser-beamed energy microspaceships. If you would, explain the concepts involved and their benefits.
Yes, so we received a NIAC award in July of this year, 2015, and the basic research is to look at the feasibility of achieving relativistic speeds in a practical way, rather than just assuming miracle happens here and we get there, but rather look at it from a very hard scientific point of view and see what could be done with today's technologies or near-term technologies, rather than waiting for wormholes, antimatter drives, or other currently non-existent technologies. So the basic goal is to look realistically at the ability to achieve relativistic flight, which is a necessary precursor technology to any interstellar flight. So the basic idea here is the opposite of what American Express says, which is don't leave home without it. So our statement is don't leave home with it, and it being the propulsion system. So do not take your propulsion system with you, as to do so will prevent any realistic journey to the stars from taking place. And the reason being that all current propulsion systems are very massive and require propellant of some sort, and transporting that propellant basically is a non-starter in any interstellar flight currently envisioned, that's realistic anyway. So our approach is to leave the propulsion system at home and project the energy to the spacecraft and drive the spacecraft up to relativistic speeds. And by leaving the propulsion system at home, we can have extremely low mass spacecraft, which allows us to achieve extremely high speeds. And we're using some very recent advances in technology, basically that are photonic in nature, i.e. the conversion of energy, electrical in this case, into light to drive the spacecraft to high speeds, somewhat akin to what people may be more familiar with, known as a solar sail. But in this case, we're using a directed energy-driven sail, which is appropriate for achieving relativistic flight, whereas a solar sail will not get you to relativistic speeds and will not be useful for interstellar flight. It's useful for other things, but not for interstellar flight. It's a good precursor.
There's a possible confusion for some people, the concept of light sail. Because they hear so often about the solar wind, that they associate the light sail as grabbing a hold of that solar wind, when of course it's not. It's the photons, the light from the sun. And this is a case of that too. So you're taking advantage of the laser. Would you talk a little bit about that?
Light, like any form of energy, carries with it momentum, and that momentum can be used to push against something. In our case, that something is a reflector. When you turn on a flashlight and point it at the wall, you are being pushed back and the wall is being pushed away from you. You don't perceive that because the force is quite small for the levels of flashlights which you have. But a large system and a low mass wall could actually achieve relativistic speeds, at least on paper. The difference between this approach, where the flashlight is actually a, a, a special type of laser, a laser array, and something like a solar sail, which drives a reflector light from the sun, is basically a matter of intensity or power per unit area on the sail, and the distance to which we can propel a spacecraft with sufficient force. There's a related topic, which is the sun emits, in addition to photons, also emits particles, which we sometimes call the solar wind. The solar wind consists of material ejected from the sun and accelerated away from the sun, and that too could be used in theory to propel an object. But the force from the solar wind is quite small, first of all, and drops off extremely rapidly with distance, basically is the inverse square from the sun, and is not sufficient to drive a spacecraft to relativistic speeds. It's useful for exploring inside the solar system, i.e., solar sails and some variants of the solar wind, e-sails, for example. So those are very useful for inside the solar system and could, achieve mild speeds, but not relativistic speeds, for exploration, slightly outside the solar system. But they're not suitable for true interstellar travel.
Let me ask you about the microspaceship itself. By removing the propulsion, you're able to make a spaceship that's very, very small. If you would describe the microspaceship, its size, maybe its components or instrumentation.
So the lower the mass of the spacecraft, and the higher the speed that you can achieve. And that seems reasonable and logical to most people. When you write it down mathematically, as we've done in our papers, you see very quickly how the scaling of speed with mass goes. But basically, you can imagine something which is lighter goes faster for a given amount of force. That's quite logical. So in our case, we're looking at a range of spacecraft sizes. Our approach will drive any size spacecraft, but the lower the mass of the spacecraft, the higher the speed, the higher the ultimate speed. So this technology is useful over an incredibly large range of spacecraft masses, from a human crewed spacecraft, which could be used inside the solar system, to extremely small, which we call wafer sats, which are basically wafer scale satellites that are literally the size of a silicon wafer or a other semiconductor wafer on which we put the basic elements of a spacecraft onto a wafer. So in that case, the wafer mass is of the order of 1 gram, which is about the same mass as a cubic centimeter of water. And the speeds that could be achieved are vastly greater than a typical spacecraft that you might imagine. So one of the challenges is reducing a functional spacecraft to a semiconductor wafer. But with new technologies, it's quite possible to put many of the elements you might associate with a spacecraft onto a wafer. The number of devices you can put on a wafer is quite staggering if you imagine what's inside your computer, which is a tiny fraction of a wafer. Your modern processor has of the order of a billion transistors on it, some which is used for memory and other functions. On a wafer, you can achieve over 1 trillion uh, devices or transistors with current technology, and that will, of course, only get better with time. So if you imagine a trillion transistors, what could you do with a trillion devices? You can do all kinds of things. You can do imaging, you can do laser communications, you can do sensing of magnetic fields and radiation, you can do navigation, you can even do photon thrusting with embedded LEDs or small laser chips. So there's all kinds of interesting things that you can do, and so we have a part of the program is to reduce spacecraft to a wafer. And again, this is only appropriate for certain classes of spacecraft. You wouldn't imagine putting a human crew onto a wafer unless we can really get the shrink me ray working, which I don't know how to do currently. Although, what's his name in Despicable Me does seem to know how to do that, but we have to talk to him first. But we could put all kinds of other things, including precursors of life on board, our genetic information, etc., in both physical and digital form. So one of the challenges that we're looking at is putting a spacecraft onto a wafer. But again, keep in mind, because this does get confusing for people, we can drive any mass spacecraft. It's just higher masses go slower. So we can drive a CubeSat up to mildly relativistic speeds. We can drive a 100-kilogram class spacecraft, which is roughly of the order of the Voyager mission, up to more than 1,000 kilometers per second, which is nearly 100 times faster than Voyager is currently going. And we can drive a crewed mission to Mars, so that one could imagine going to Mars much more rapidly than we're currently going. We can have overnight delivery to Mars, literally. We can have FedEx to Mars with small packages. There's all kinds of interesting possibilities that come from this technology, not just one. I know people are often very interested in achieving the highest relativistic speed possible to get to the nearest stars as quickly as possible. But this technology is completely scalable, both in its technological base as well as the spacecraft it can drive. So that needs to be understood to properly appreciate what basically really revolutionary changes can come from approaching uh, space transportation in this way. It's not suitable for all forms of transportation by any means, so we don't say that it is. But it is the only way I know of, to achieve relativistic speeds and to have any realistic hope of getting to the nearest stars in sort of a human lifetime scale. And while people would love to build what do they call world ships, or a large spaceship, something like we see on Star Trek and Star Wars, which would be fabulous. It doesn't exist. That technology just simply does not exist currently. So as we state in our papers, and people might want to look at our paper called A Roadmap to Interstellar Flight, where we lay out the technology and a lot of the background discussion. We could either give up our dreams of going to the stars, or we could look at what realistic approaches there are to going to the stars and work towards that goal.
One of the key differences between this and propulsion systems that people are familiar with is that this is a continuous propulsion where they're accustomed to seeing the engine, say, on a rocket burn for 2, maybe 3 minutes, and then turn off. And this is very different from that. Talk about that, if you would, please.
Actually, it's not that different.
Mm-hmm.
And let me give you a good example. I'm sure everyone in this audience is familiar with the former space shuttle
Mm-hmm.
system, which is a wonderful system. The burn time on the boosters for the space shuttle are on the order of minutes. For the SRBs, or the solid rocket boosters, the large things on the side that come off, and then another 5 to 10 minutes on the main engine um, to get to orbit. So roughly time to orbit, is of order 10 minutes, roughly. Now, if you compute the amount of power that it took to put the shuttle into orbit, rather than just looking at the thrust in terms of meganewtons or pounds of force at liftoff, but if you actually look at the power, which is not stated in the official NASA literature at all, but turns out the power that the shuttle has at liftoff is around 50 gigawatts, where a gigawatt is roughly the power of a nuclear power plant. So 50 gigawatts. And that is on for, again, of order, a few to 10 minutes, and lifts a craft the size of the shuttle into orbit. That's the reason I mention that is actually there's a very relevant discussion here. Um, if you compute the energy of the or kinetic energy of the shuttle in orbit, it's of the order of a small tactical nuclear weapon, so of the order of a kiloton of TNT equivalent. Now, in the case of our system, we actually do something similar. We turn on the laser or directed energy system, shine it onto the reflector, which can have multiple bounces or one bounce depending on the mode that we run in, and that's a technical complication we'll talk about later, perhaps. Certainly in my talk I'll discuss it. And it's only on for a limited period of time. Actually, in the case of the wafer satellite, it's on for a few minutes, literally. Turns out to be very similar to the space shuttle. Uh, it's on for of order 3 to 10 minutes, and then it's off. That's it. You're going ballistically after that, and so we don't keep the laser on continuously. There is I agree there is a misconception there that many people have. We turn the laser off, and what do we do with it? We get ready for the next launch. So the nice thing about this system is you amortize the launch system, namely the directed energy laser, over many, many launches. So we could literally launch a spacecraft every 10 minutes if they were of the wafer sat size, and if the launcher was of the size that we would need to build, which, by the way, um, again, the shuttle takes about 50 gigawatts to lift off. Our system, to get to relativistic speeds in order to get to the nearest stars in a time of order 20 to 40 years, would also require about 50 gigawatts and would be on for a similar period of time, about 5 to 10 minutes. But in our case, instead of having a shuttle launch every few months at an enormous cost, what we do is the cost goes into the directed energy launcher, and then you can literally launch a new wafer sat every 10 minutes if you want. Or you could take that same launcher, the exact same launcher, and launch a CubeSat up to a few percent the speed of light. The wafer gets up to about 20 to 30% the speed of light. Or you could launch a 100 kilogram class, Voyager class spacecraft, which these, in the larger mass cases, as you might imagine, the laser stays on longer, but not indefinitely. Or you could launch, a 100,000 kilogram class spacecraft, which is actually larger than the shuttle, um, but of that order anyway. And send it within the solar system. Again, larger mass is slower. So if you want to go to interstellar distances with the kind of technology we're talking about, you can scale up to even larger sizes than we're discussing, but the ones we're discussing are already quite large. So in theory, you can keep scaling because there's no current scaling limit. That's I mean, there are some, but they have to do with technical issues rather than fundamental issues. So that you could, as you want to launch larger and larger mass systems to higher and higher speeds, you can just keep adding onto the system because it's a scalable and modular technology, unlike many technologies we have today. For example, if you look at at the SLS, the upcoming SLS launch system, it's looks similar to a Saturn V, and looks similar to many of the other launch systems around. Yeah, but it's not the same. You don't just simply add on the same components. Whereas in our system, it's basically you just keep adding the same thing, and all the sub elements are identical. And you're already getting close to unity efficiency, so you're not going to do a whole lot better in the future. You'll do a bit better in efficiency. The efficiency is running currently around 40%, and it's pushing 50%, but currently about a little over 40%. So you'll do a little bit better, but we're already getting close enough to one that you're not going to do that much better no matter how hard you try. But what does get better with time is the mass goes down of the launch, the directed energy system mass goes down, which makes it easier to put into orbit, or put on the moon or wherever you want to put it. And by the way, it's It could be put on the ground. It could stay on the ground, but we have to figure out a way to deal with the atmosphere in a way that I currently don't know how to deal with. It's a much more than a normal adaptive optics problem. It's vastly harder than that.
You paint a beautiful picture. I'm imagining almost a cloud of micro spaceships leaving our solar system in every direction to perhaps hundreds of stars. Do you have that kind of vision? Is that within the scope of your estimation?
Yes. Yes, absolutely. So our vision is to literally amortize this launch system so that we could launch literally tens of thousands of spacecraft per year, of all sizes. And of course, the smaller the spacecraft, the more of them you can launch, per unit of time. So in the WaferSat case, you could literally launch over 100 per day, or more than 40,000 per year. So yes, our vision is to launch enormous numbers of these and to keep launching them. This is a completely solid state system, so it has a very long lifetime at least in theory, and it's repairable. So part of it breaks. It doesn't have the nominal single point failures that a lot of systems have. If one sub element blows out, it doesn't really affect the system very much. So yes, that is our vision.
Excellent. Thank you, Doctor. I sure appreciate you taking time for the interview.
Yeah, no problem. Thank you.
That was Dr. Philip Lubin, Professor of Physics at the University of California, Santa Barbara. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please click the like button, and you can subscribe to our channel for more such videos. On behalf of all of us here at the Tennessee Valley Interstellar Workshop, I thank you.